In section 3.6, the first section is about direct variation. Direct variation is basically a line where it starts, the line's going to start at the origin and be a straight line. So those are the two requirements for a direct variation. And when we have a direct variation, this is my x-coordinate, this is my y-coordinate, and that can be expressed in these three equivalent statements. So you can use the equation y equals kx, and you can see how that would be like a line where the slope is equal to that k. And y varies directly with x. That's another way to say that we have this relationship where we start at the 0, 0 and have a straight, direct line. And y is directly proportional to x is the third statement. These three statements are equivalent ways of saying that we have a situation modeled by this graph. The thing that changes is the value of k. K is called the constant of variation or the constant of proportionality. So that tells us how steep this relationship is. But basically it's saying as x goes up, y goes up by k. So let's look at what this looks like in a real life example. So we want to look for the mathematical model describing the monthly long distance bill if the cost is directly proportional to the number of minutes. And the customer that used 160 minutes is billed $40. So let's look for one of these equivalent sentences to see how to model this. So let's see. Let's read this again. The cost is directly proportional to the number of minutes. So that is like this third statement. And that tells me that y, that's how we start, the cost, so that's the y. Y is the cost, and is directly proportional to the number of minutes. So y is directly proportional to x. So that means x equals the number of minutes. So k will be the constant of proportionality that tells us how much the bill goes up with every additional minute. So that is your slope. It's the additional cost for every minute. It's the cost per minute. And you can think of that as slope as thinking about changing in y over change in x. So if our y is cost, then our x is minutes, then we have our change in cost over the change in minutes. So now the information I'm given is that there is a point at, so I know x is minutes, so this is minutes over here. So when I have 160 minutes, then the corresponding cost is $40. And since direct variations always start at the origin, I can find that k, thinking about it as slope, and it's always y over x. Since it starts at the origin, the rise is $40 and the run is 160 minutes. So k equals dollars per minute, so that's $40 for 160 minutes. And reducing that, I get, let's see, what do I get? I get $1 for 4 minutes, or 1/4. So my equation is always in this form, y equals kx. So my generic equation is a y equals kx, and I replace the k with my specific k for this situation. So that's similar to that slope-intercept form where I have kind of that standard and I just have to fill in the slope and the intercept, except here this intercept is always 0, so I just have to fill in the slope, which is k. So there's my mathematical model describing that long-distance bill. All right, so in your homework exercises, you'll ask questions like, write an equation that describes each variation. So that brings us back to this equation right here using either of these words. So in this sentence we have S varies directly with T, so that is what, like similar to Y varies directly with X. So S is the Y and T is the X, which, looking back at the equation, gives me S equals KT. And then to find to find that equation, I would just have to search for the K. All right, then sometimes I might have something like this, where it's actually varies directly with a power of X, in which case I get A varies directly with, so that's my constant of variation, that's my varies directly with, x squared instead of x. So where x squared is my, would be my axis, I would actually have an x squared on that horizontal axis instead of x. So direct variations with powers. So for example, children's growth. You know, if children had a direct, as you grow older, you grow bigger. And if that was proportional, if all your body parts were growing proportionally at the same rate, at that direct, let's look for that lingo, directly proportionally to each other, then babies will just look like mini adults. But they have a different proportion. They have those big doughy eyes, and they have big heads, and tiny little limbs and big thighs, and they have so their different body parts actually grow at different rates, and that is an example of something that might vary directly with a power of x rather than x. All right, so that is another example of a direct variation. So that wraps it up for the 3.6.1. Okay, I changed my mind. I'm actually going to do one more example from the little second set of your homework. So in this example, number 18, we have F is directly proportional to M. So that tells me F equals some constant, constant of proportionality, M. So F and M are our variables, and K is the constant we need to find. So we can use the fact that we have this point when F equals A, then M equals 1. And we can use that to find out what K is going to be. So solving for K, I can divide both sides by 1, and I get K equals A, which gives me an, so A is actually a constant. So I get F equals A M, where A is my constant of proportionality.